Swayam Prabha. Digital India. Educated India.
Welcome to another lecture of this course, Mathematics for Economics Part 1. So, in the last lecture, we have covered a topic called optimization with a single variable. We are going to start with a new topic today, it's integration. Now, integration, as we shall see, it's the opposite of differentiation that we have discussed earlier. And like differentiation, integration also is a very important tool of economists and people associated with financial analysis. So, today we are going to start with this new topic, introduce a few definitions and concepts, and then we shall see what we can say about the applications. Okay, as this is the first slide you can see on your screen, and first we are going to interpret integration as area under a curve. So, that is going to be the interpretation of what we mean by integration, area under a curve. Okay, so this is the first question that we are starting with: how to estimate the area on a plane which is not enclosed by straight lines on all sides, right? This is a very old problem. The Greek mathematicians dealt with this problem, so you can understand it's a very ancient problem that has been challenging human mind. If you have an area which is enclosed by straight lines, okay, like this, it is relatively easy to say something about the area enclosed by these straight lines. But if you do not have straight lines on all sides, then it becomes a little bit difficult how to estimate the area enclosed by those lines. And there are practical implications of finding the area which is enclosed by lines, maybe straight, maybe non-straight. Think about surveying the land, right? Different farmers might be having different plots of land, and those boundary lines may be straight lines, may not be straight lines, but as a surveyor you might be interested to find out what are the areas that are owned by different farmers. Not only farmers, every landowner, irrespective of being farmer or not a farmer, might be having lands, and the administrators might be interested to find out the areas owned by different landowners. Why? One reason could be the land taxes are imposed on area of the land under your ownership. So, as a surveyor, as an administrator, you will be interested to know the area of land owned by different landowners. So, this question of finding the area enclosed by different lines has very important practical implications, and that is why the ancient thinkers were grappling with this problem. Okay, here is the diagram that I have on the screen. you can see that I have a curve fx, okay, and I have taken 2 points on the x axis A and B, right. Now, from point A one can find out what is f of A, this is f of A and this will be f of B, okay. So, in essence you have one side here, one side here and one side here. All these three are straight lines, but on the top you do not have a straight line, you have the curve, and this curve can take any shape, right. Only thing we need is that this y is equal to fx curve or this function, it is positive valued, right. We are on the first quadrant, so fx is positive valued. It is continuous, right, it is a continuous function, otherwise there will be gaps and there will not be a continuous line which will be enclosing an area. There will be no enclosure if you do not have a continuous line. Okay. So, the question that we are asking is this: given 2 points A and B on the x axis, what is the area between A and B and below the curve? So, this and this below the curve between A and B, this entire area we may be interested to find out this area. Okay. So, that is the question that we are starting with, and as we shall see, integration actually is a tool which will give us an answer to this question, the area between 2 points and below a particular graph. Okay, let us start with an assumption. The assumption is that, let us suppose this area is given by capital A, okay, and let us define a function which measures the areas under the graph of y is equal to fx as follows. So, if you have a function y is equal to fx and this is the x axis, and let us suppose this is your A, this is B and this is x axis, right. You are defining something called Ax. What is Ax? Area under fx between A, this point, and x. X is any arbitrary point and this x is less than B, right. Suppose x is here. So, this area, let me shade this area to demarcate it. This shaded area, we are calling it as A of x. Okay. So, that is what I have written here. A of x is the area under fx between A, right, A is one point, and x, x is another point, and obviously x is greater than A. Now, from this definition of this area A of x, obviously you take the two end points. If you take capital A of small a, that is, you find out what is the area between small a and small a, right. Between small a and small a there is no area, it is 0. Okay. That is one extreme. The other extreme is capital A of the end point here B. Okay. So, A of B will be equal to A. What is A? A, mind you, was the area. So, the complete area was defined as A, capital A. So, pardon the symbols that I have used, there are repetition of the same letter, right. So, just to clarify, between small a and small b, the area under the curve is given by capital A, right? And that is why if I take this function a, so capital AX is a function. If I take capital A of B, then I get the entire area, and that is equal to capital A. Alright, so these are the boundary points. Since Fx is positive, right, Fx is positive, that is we are in the first quadrant, it is positive valued. As x increases, this function also increases. The area that we are talking about, as you are moving to the right, you are raising the x, and since the function is positive valued, so the area under the function will rise, and therefore capital AX increases. So that is one important property. Okay, we have defined a function. So sum total of this is that we have defined a function capital A of x, which basically measures the end area under this particular function Fx between small a and small x. Okay. Now we are going to play around with this function capital A of x. Let delta x be the change in the value of x. Then the change in the function is given by delta A. Okay. Delta A will be the change in the area, and that is given by the new area, which is A of x plus delta x minus the old area, which is A of x. So what we are talking about is this extra area delta A. Okay. Just to clarify, we started with this x point, and we know A of x is this area, right. Let us use a different shade. This is A of x, all right. Now suppose x rises by how much? By delta x. So the new value of x is this much, x plus delta x, all right. And the new value of the function is how much? Functions means the A function, it will be A of x plus delta x, this shaded area plus this shaded area, right. That will be capital A of x plus delta x, okay, because this is the new value of the independent variable. Now we want to find out what is this area, this delta A area, that is the increment in the area. So that is delta A, and that is given by this expression capital A of x plus delta x minus capital A of x, right. That is simple. You are taking the whole and then subtracting the left hand side shaded region, right, and then you are going to get this slanted shaded region, which is delta A. This is the area under the curve in the interval x and x plus delta x, right, that we have shown in the diagram. This delta A is under the curve, under Fx, and between two values which are x and x plus delta x, right. That is very clear. Now these are some of the important relationships. We have to understand that delta A is greater than or equal to delta x multiplied by Fx. So what is this saying? Remember, what is delta A? Delta A is this entire slanted shaded region. This is delta A. What is being said here is this area will be greater than delta x multiplied by Fx, okay. That is what which is being claimed. Now what is delta x multiplied by Fx? What is the meaning of this claim? Well, delta x is the base. Okay, this is delta x, and what is fx? Fx is this height. So, when we are saying delta x multiplied by fx, what we have in mind is this rectangle, the area of this rectangle, right. This rectangle's area is given by delta x multiplied by fx. And we have in this example taken an increasing function. So, we are saying that delta A, which is the area under the curve, right, that should be either greater than or equal to the area of this rectangle, right. If the function is not an increasing function, if it is a flat function, it is a, think about a horizontal line. In that case, these two parts, left hand side, will be just equal to right hand side, but since we are considering a mildly increasing function, so we are writing as this as an weak inequality. Okay, this is what this relationship is saying. Delta A, which is the area under the curve in this particular interval, is greater than or equal to the area of the rectangle, where the height is fx. Okay. And you have another relationship, similar relationship I should say, which is saying that delta x multiplied by f of x plus delta x is greater than or equal to delta A. And this is just similar in the sense that concentrate on the left hand side expression delta x. What is delta x? Again the base of this rectangle. And what is f of x plus delta x? It is this. This is f of x plus delta x, this height. So, when you are writing this expression delta x multiplied by f of x plus delta x, what you have in mind is the area of this bigger rectangle, right. So, earlier the rectangle was this rectangle, now this one was the smaller rectangle. Now, when you are expressing this, you are talking about a small block which has been kept above the smaller rectangle, and you have a longer rectangle. Okay. And what is being said as is this is greater than or equal to delta A. Okay. And that is obvious. What is delta A? Delta A is area below the function. So, that is the right hand side, but on the left hand side what you have the area below the function, but you have something extra. Okay. That is why this should be greater than or equal to delta A. Why equal to? Well, greater than one can understand, it is obvious. Why equal to? Again, the reason has to do with the fact that this fx function could be a horizontal line, right. If it is a horizontal line, slope of 0, then you actually have an equality. You do not have any inequality, you have an equality, and that is why to make that possibility felt here, we have a greater than equal to sign here. So, these two things are correct. Both these two things are correct, and we can combine these two relationships in a single relationship actually, because delta A is common to both of them. Combining these two, we get this, right. Just to make sure whether we have done it correctly, delta x multiplied by fx plus delta x is greater than or equal to delta A. Yes, that is true here. It is coming from here, and delta A is greater than or equal to delta x multiplied by fx. That is also coming from here. So, both these things are correct. Therefore, I can write this as a chain. This chain is saying that delta x multiplied by f of x plus delta x is greater than or equal to delta A, which is greater than or equal to delta x multiplied by fx. Okay. Now, I am going to use the something which I have just found out earlier, that delta A can be written as this, A of x plus delta x minus A of x, and this is something we have talked about earlier. I am just going to substitute this in this place. All right. And next we divide all these three expressions by delta x. I can do that legitimately because delta x is not equal to 0, it is the increment. So, it is not equal to 0, so I can divide all these three terms with delta x, and then I shall get this expression f of x plus delta x is greater than or equal to A of x plus delta x minus Ax divided by delta x greater than or equal to fx. Now, I take the limit of delta x going to 0 in this entire relationship, right, in this chain. Now, if I concentrate on the middle portion, the second term, as delta x goes to 0, what happens to this? Just notice what is this term, the middle term. This is nothing but the Newton quotient. Okay. And as delta x goes to 0, I know what happens to the Newton quotient. It becomes the derivative of this function. Which function? A of x. So, it becomes A prime of x. So, d dx of Ax, that is what it becomes, the second term. Okay, that happens to the middle term. On the other hand, both the left and the right hand sides approach fx, right. This is obvious. As delta x goes to 0, this term, that is f of x plus delta x, will go to f of x, and this is the first term. Whatever the third term is independent of delta x, so it does not change at all. So, in a sense, both the first term and the third term approach f of x, whereas the middle term approaches A prime of x. All right. That is what happening to the three terms. The first term and the third term approach the same value, which is fx. And so, assuming the function measuring the area between A and x below fx is a differentiable function. Okay, that is important. So, I have to assume that Ax is a differentiable function, otherwise I cannot take the derivative of it. Now, if it is differentiable, then the derivative of then this this term will become equal to A prime of x, that is A dashed of x, and that will be equal to fx, because fx is what the first term and the last term are converging to, approaching as delta x goes to 0. And this will be correct for all x in the interval a to b. Remember, just to remind you, x is always in this interval. It is not greater than b or neither it is less than a. And we have shown, and this is a very important result, we have shown that as long as x is between a and b and fx is a continuous function, then there is this area function which is we are representing by A of x. The derivative of that area with respect to any x between a and b, that is A prime of x, will be equal to the value of the function, which is the fx. So, that is the end result of this exercise. A prime of x is equal to fx. What is A prime of x? The derivative of the area under the function, right, under the fx function. That derivative of the area is equal to fx. In other words, the derivative of the area function, that is Ax is the area function, derivative of this gives the value of the function, which is fx. This demonstration that we have just done is not dependent on the assumption of fx being an increasing function. For other kinds of functions, a similar argument can be made. So, what is being claimed here is that in this demonstration, we have drawn the fx to be an increasing function, and then we have shown that a dash of x is equal to fx, right. Now, the questions that can be asked is that suppose fx is not an increasing function, then can we claim the same thing? Can this claim of a dash x is equal to fx be maintained if fx is not an increasing function? And the answer to that is actually yes. Even if fx is not an increasing function, it can have other kinds of nature. In those cases also one can show the same thing. The demonstration will be similar if not the same. If Ax is an area function, okay, now we are talking about something a little bit complicated. Suppose Ax is an area function, let fx be another area function with the property that f dash of x is equal to fx for all x belonging to this interval a to b. All right. Suppose there is another function also fx for which the same relationship holds. Same relationship holds means, remember, for Ax, a dash of x is equal to fx. But suppose there is another function fx for which also f, that is capital F dashed of x is equal to small f of x for all x belonging to a to b. Now, if this is correct, so what you are essentially saying is that f dashed of x is equal to fx, at the same time a dashed of x is equal to fx. Therefore, from these two I can conclude that f dashed of x is equal to a dashed of x. Now, f dashed of x is equal to a dashed of x, that means f x plus c is equal to a of x, where c is an arbitrary constant. How am I saying this? Because you take this relationship and you take the derivative of this, what do you get? This will just become f dash of x because c will become 0, derivative of c is equal to 0, and this is the left hand side. On the right hand side also you take the derivative of ax, it becomes a prime of x. So, f prime of x is equal to a prime of x. From that I can actually write f x plus c is equal to ax. Okay. Now, put small x is equal to a, right. If you put small x is equal to a, then on the right hand side I know what is a of a, it is equal to 0. That is how capital A, this function has been defined. So, therefore, f of a will be equal to minus c, right, because f of a plus c is equal to 0, therefore, f of a will be equal to minus c. So, f of a is equal to minus c. All right, and therefore, I can write f x minus f of a is equal to ax. I have just substituted, in case of c, I have substituted minus of f a, right, in this relationship. Therefore, I get capital A of x is equal to f of x minus f of a. Now, what is the implication of this relation? A of x is equal to f of x minus f of a. What it means is the following. To find the area below y is equal to fx between a and b, and above x axis, find an arbitrary function f(x) which is continuous in a to b, right, and such that this relationship is maintained, that f dash of x is equal to f of x for all x in a to b. So, this is the first thing that we found, and there if I can find such a function, then the required area will be fb minus fa, okay, that I have just seen here, because remember fx, capital F of x, is a function which is such that f dash of x is equal to fx, and there is another function a of x which is defined in such a way that a of small a is equal to 0, and using this function and using the relationship this, I have found out that a of x is equal to f of x minus f of a, and from this I can get what? A of b is equal to f of b minus f of a. And what is a of b? It is nothing but the area that I wanted to find, and therefore capital A, which is the required area, is equal to f of b minus f of a. That is what I have written here, f of b minus f of a. So, this is the algorithm. This is the important thing that we have to remember, that if you want to find out the area below a particular function which is given to us, continuous function y is equal to fx, this function, between a and b which are given to us, small a's value is given, small b's value is given, then firstly we find another function capital Fx such that capital F dash of x is equal to small f of x for all x in this interval. And if I can find such a function capital Fx, our task is done. We have to just evaluate this function at b, evaluate this function at a, and take the difference. That is it. Okay. So, that is what this interpretation of area under the function is telling us. This is called, as we shall see, this particular f function, capital F function, will be called the integral. The function capital Fx with the property f dash of x is equal to fx is called the antiderivative of fx. Why is it called antiderivative? Well, if you have this capital F dash of x is equal to fx, right, and suppose how did I get capital F dash x? I took d dx of fx, right. I took fx and take the derivative of that, then I got f dash of x, and that is equal to the function that we are given, which is small fx. So, to get back to capital Fx from small fx, I have to do something which is opposite to take the derivative, right. I have to go from here to here. So, to do that I have to reverse the process of differentiation. That is why it is called antiderivative of small fx. Okay. Now, interestingly, there can be infinite number of such functions, that is fx, capital Fx, which satisfies the property, this property. There can be infinite number of such functions, because think about the constant term, capital Fx plus c, c is the constant term. For all these functions, you take different values of c, you will get different functions from here. Now, for all these c's, if you take the derivative, then you will get f dash of x, right, and that f dash of x is equal to small fx. So, I am not sure which capital C is the right capital C. In fact, there are infinite number of capital C's which will satisfy the same condition, and all of them are valid. And later on we shall see that we can get around this problem by something called an initial value. Okay, an example is given here how to find the area below a function between two particular values. Find the area below this function which is given to us y is equal to x cube. Okay, this is given to us below this function and between the point 1 and 2. So, as we know, what was the algorithm? We have to find another function such that the derivative of that function is equal to x cube and then use that function. That is what we have to do. The derivative of the function that we find should be equal to x cube. And you can do some trial and error, and you will ultimately find that if you take capital Fx is equal to 1/4 of x to the power 4, then the derivative of that is this function will be equal to x cube. You can just verify that, right. So, you take the derivative of 1/4 of x to the power 4. So, you use the power rule, it becomes 4 of x cube, and that is x cube, right. So, and that is what the function which is given to us. So, this is the function we want to find the antiderivative of x cube, and the last task is quite simple. I have to evaluate this function at 2, this is f of 2, and from that I have to subtract the value of the function at 1, and that we are doing here, that is 1/4 of x to the power 4, that is 2 to the power 4 is here, minus 1/4 of 1 to the power 4, right, the values are 2 and 1. And then we simplify this bit and we get 15 divided by 4. So, just to make sure how this looks like. So, here you have the y. Think about the shape of this function. At x is equal to 0, this function will give you a 0 value. So, it passes through the 0, 0 point. It does pass through the 1, 1 point, and then it becomes convex function. It is always a convex function, it becomes steeper and steeper. So, here is your 1, 1, and let us suppose this is 2. If you put x is equal to 2, then 2 to the power 3 is 8. So, here is 8 and here is 1. So, the area that we are talking about is this area, right. As you can see, it is not an area enclosed by only straight lines. On the top you have a curve, and on the 3 sides you have straight lines, but fear not, we can actually find out the area by this method, and it comes out to be 15 divided by 4. So, what is the approximate value of that? This is a little bit less than 4, because had it been 16 divided by 4, it would have been 4. So, it is a value a little bit less than 4, but obviously greater than 3. Okay. Now, the important question that may arise here is that what happens if f(x) takes negative values? Okay. What does it mean? It means that we are going into the 4th quadrant. So, you have f(x) here, and here is the 4th quadrant. Suppose f(x) takes this kind of shape. So, it goes to the negative territory. Then does the same formula apply? Can we use the same method to find out the area, right? Now, what will happen if we apply the same method? It will give the area as a negative quantity. So, if you want to find out suppose this area between this point and this point, this is the area. Now, if you blindly follow the same method as before, you are going to get a negative quantity. Now, to correct this, what we define the area to be is the negative of what we thought would be the area by our previous formula. So, negative of capital F of B minus capital F of A. This is the method that we should apply, because if we do not add this negative sign, then the area will come out to be negative, which is absurd. So, we apply this formula where fx can be negative between a and b. So, here is an example of how we do it in practical terms. Find the area below the x axis and above this function y is equal to x square minus 4 and between 0 and 2, x is equal to 0 and x is equal to 2. So, small a and small b are given, fx is given. Now, we have to just find the area. Okay, let us think about this function a bit to see how it looks like. Alright, we know at x is equal to 0, what is the value of the function? If you put x is equal to 0, it will give you minus 4. If you put x is equal to 2, it will give you just 2. 2 square is equal to 4, 4 minus 4 is equal to 0. Okay. So, how does it look like? 0 minus 4 and 2, 2 is somewhere here, let us suppose 2. And so, this function is going to go through this point and this point. Okay. How am I sure that it is going to be a convex function? I have drawn a convex function. How do I know that it is a convex function? Well, you just take the second derivative of this function. Second derivative is 2. So, 2 is a positive number. So, it is a convex function. It is a convex function and it passes through these 2 points 0 minus 4 and 2 0. So, this basically the main point that I am trying to make is that this basically goes to negative territories. So, I have to apply this formula rather than the formula that we have talked about before. Now, in this new formula or the new method, like the old method, I have to first find out fx such that f prime of x is equal to x square minus 4. So, how do I do that? Okay, I assume a particular form, right? Fx is equal to, let us suppose, a of x to the power n minus b of x to the power m. You see, it is a very general form, polynomial form. I do not know the value of a, n, b, m. I have to find those values. What I know is that if I take the derivative of this function, then I will get x square minus 4, which is the given function to us, x square minus 4. That I know. Now, from the assumed form, which is x to the power n multiplied by a minus b of x to the power m, if I take the derivative of that, that is f dash of x, I will get a n x to the power n minus 1 minus b m x to the power m minus 1, and that I know is equal to x square minus 4. Now, the next task is relatively easy. I just have to compare the coefficients and the powers. Now, if I compare the coefficients, then n minus 1 should be equal to 2, right? This will straight away give me the value of n is equal to 4. And I also know that m minus 1, right, x to the power m minus 1, here the power of x is 0. So, m minus 1 is equal to 0. X's power 0 is because there is no x here. So, m is equal to 1. So, n and m are found out, and using that I can now find out what is b, because minus b multiplied by 1 is equal to minus 4. So, b is equal to 4, and a multiplied by 3 is equal to 1, which means a is equal to 1 divided by 3. So, everything is now clear to us. I have found out n, I have found out m, I have found out b, I have found out a. Now, I substitute them back to the assumed form, I will get this function. So, it is 1/3 of x cube minus 4x. And one can actually verify that this will, if I take the derivative of this, what do I get? It becomes 1/3 multiplied by 3x square minus 4, that is x square minus 4. and that is what is given as the small fx. So, we are on the right track. Now, comes the last part, which is I have found out capital Fx, but since the values are negative, values of fx, small fx is negative, then I basically take the negative of f of b minus f of a, right, minus of f2 minus f0. If I multiply by the negative sign, then I get f of 0 minus f of 2. And now I use this particular form that I have found out. And if I do so, then I know f of 0 will be equal to 0. This will give me 0. What about f of 2? Well, 1/3 of 8 minus 4 multiplied by 2, and that will be what? That will be minus of this, that is 8 minus 8 by 3, which is equal to 16 divided by 3. So, that is the area. Let us see how, if it makes sense or not. 16 divided by 3, what is the value of 16 divided by 3? It is a little bit over 5. Okay. Well, look at, we are talking about this area, right. So, what is being said is that the area under this curve is 16 divided by 3. Okay. In a similar vein, if the function alternates between positive and negative values and one wants to find the area enclosed by the curve with the x-axis, one needs to subdivide the range into smaller intervals. So, suppose the function is such that it snakes around the x-axis like this, that is, it goes to the first quadrant and it can come back to the fourth quadrant, etc., etc. Then suppose you want to find the area, this, summation of all this, right. Then what do you do? Suppose we want to find the area bounded by the curve, the x-axis and the lines a, x is equal to a and x is equal to d. So, here is x is equal to a and here is x is equal to d, right. You want to find out what is the area enclosed by the function with the x-axis, that is the area between the function and the x-axis, and that is the vertical stretch. Horizontally, the stretch is from a to d. So, the shaded regions that I have demarcated on the diagram, those regions, the area of those regions have to be found out. Now, here what we do is something quite similar to what we have done before. We subdivide the entire range into smaller portions. So, we are basically first finding out those points where the function is intersecting with the x-axis. Here there are 2 points of intersection, B and C. So, between A and B, the function is taking a positive value, and between C and D also the function is taking a positive value. So, for those cases, we can use the former formula, that is, capital F B minus capital F of A, right. But between B and C, the function is taking a negative value. There we have to take that formula which was applied when the function takes a negative value, which is minus of Fb minus Fa, right. So, basically what one is saying is that we have to subdivide the entire range according to the points of intersection. All right. And finally, when we have found out these different areas separately, then we add up these areas and we are going to get the final result. Okay. So, this is the method. So far, what we have done is that we have not used the word integration or integral, right. We have talked about area under the curve. Right now, we are going to start with this idea of integrals. We are going to use this term. the antiderivative, we have talked about antiderivative. This capital Fx was the antiderivative of small fx. The antiderivative of the function fx has been defined as capital Fx such that capital F dash of x is equal to small fx. Now, this antiderivative is also called the indefinite integral of fx, and it is denoted by this sign. So, this is the integration sign. It looks like the letter S in English, but sort of elongated S, and then you have fx and dx. This is called indefinite integral of fx. Now, remember, if this is true, if f dash of x is equal to fx, then there are host of function. For all these functions in that group, this will be satisfied because you can just add a constant term. That arbitrary constant term will give you different functions, but for all those functions, this property will be satisfied. So, due to the presence of a constant term, one writes the indefinite integral as follows, right? This is what one writes: integration of fx dx is equal to capital Fx plus c. So, capital Fx is the antiderivative of small fx, but capital Fx is not the function that one is looking at because there could be a plus constant term. So, here is an example. So, x cube, if I take integration of that, so integration of x cube dx is equal to 1/4 of x to the power 4 plus c. Why? Because if I take the differentiation of this function on the right hand side, I will get x cube. That can be easily verified. You take the derivative of 1/4 of x to the power 4, what you are going to get is 1/4 4 of x cube, power rule plus 0 is equal to x cube. So, that is what I was trying to tell, that if you have the integration of small fx dx is equal to capital Fx, then that basically means that there is a constant term there, and depending on the value of the constant term, you can get different antiderivatives. So, this is in this relationship, integration of fx dx is equal to capital Fx plus c. What is the pattern that one is following when one is writing this integration, the indefinite integral? First comes the integral sign, right? We have talked about that. It looks like an elongated S. Actually, it comes from the letter S. S stands for summation. Then the function fx is occurring, small fx, and this is called the integrand, the function which has to be integrated. So, it is called the integrand. And finally, you have the c term on the right hand side, which is called the constant of integration, right. This is the last term on the right hand side. The dx term has to appear here, right. After the integral sign is there, in order to close this matter, the dx has to appear. What is the importance of this dx term? It appears after the integrand to denote that x is the variable of integration. So, it is the x variable with which the integration is taking place, right. It is like the ddx sign. So, in the case of differentiation, I use this ddx sign and x. Why do I write x? Because with respect to x, the differentiation is taking place. Here also the integration, when we do it, we have to mention with respect to which variable the integration is taking place. So, that is why x is the variable of integration. Well, now before we close, I just notice one small formula here, which is that if you take any function of the form x to the power n, right, sort of power is there on the variable, and this power is just an arbitrary power n, then it can be verified if you take the integral, and then you are going to get this form, x to the power n plus 1 divided by n plus 1, and obviously there is this constant of integration, provided that n is not equal to minus 1, because if n is equal to minus 1, then the denominator becomes 0 and this term becomes undefined. So, we have to be careful that n should not be equal to minus 1, and it can be verified easily if you take the derivative of x to the power n plus 1 divided by n plus 1 plus c. Let us take the derivative of this. It will become 1 plus n, apply the power rule, n plus 0 is equal to x to the power n, which is there as the integrand. So, this formula is correct. So, this is like the power rule formula of integration. If you take an arbitrary function x to the power n, if you want to integrate that, if you want to take the indefinite integral of that, then you get x to the power n plus 1 divided by n plus 1 plus c. C is the constant of integration. Okay, let me stop here. I am going to talk about more such rules of integration in the next lecture. Please join me then. Thank you.